In this video we're going to set up some forces and a rigid body simulation to destroy the house that we've made so far, that's fractured and got all those nice constraints in it that we've built previously. And we're going to do everything inside SOPs. If I hit tab and go to RBD, you'll see we have a RBD Bullet. Oh, let me do that again. If we go to RDB, you'll see we have an RDB Bullet solver. Let me drop this in. So in the last few versions of Houdini, they've made accessible a lot of the DOPS tools inside SOPs, things like Vellum, rigid bodies, Pyro, and the advantage of that is we can do very quick setups in SOPs. You'll notice we've set everything up in SOPs or prepared all the geometry. You can do that anyway with all those nodes. It's really handy because it sets up a lot of stuff automatically for you rather than doing it manually. But you can either feed them into one of these DOP solvers or into a proper DOP network. If you do it into a proper DOP network, the advantage of that is you can do much more complicated simulations and have different things interact properly with each other, things like smoke and cloth and etc. Whereas if you use these sort of SOP solver versions, they're limited, so I can only really do rigid bodies here. I can't get sort of bidirectional behavior between this and Pyro, for example. For that you'd need a proper sim, but for simple stuff you can do it up here. Now the exercise of this series really is to try and do as much as I can in SOPs, so I'm going to jump through a few hoops to get this to look like the actual Pyro is blowing up the house, but the wonderful thing is I'm going to do it entirely in SOPs without having to go inside DOPS at all. In fact, if I go inside DOPS and I try and make some nodes, you'll see I don't have any nodes available to me because I haven't got the FX license, which is fine, but you'll see I'll still be able to do pretty much what I'd be able to do in DOPS anyway. A bit later on in this series we'll actually look at what you can do when you go inside DOPS and how you can take this a bit further, but I wouldn't set this up this way if I was going inside DOPS, but I'll show you what I mean when we come to that, because there's a few caveats, things we have to jump through. So the first thing we want to do is just wire in these outputs to the inputs, and we'll turn this on, and our solver will start working with our bricks here. Now we're not going to see anything if we hit play because everything's all glued together. So in fact, let me just delete the glue constraint. Oh, let me plug in that one. So you'll notice there's no constraints there now, and what I want to do actually is come all the way up here to the RBD configure, and let's turn off the sleeping. Because they're sleeping, they won't move until forces actually hit them. So let's turn off sleeping so they're live. And we've turned off the glue. So in the RBD configure, if you remember, go to those tabs and turn off the sleeping in all of them. And then just break the glue connection, the constraint connection here to the Bullet solver. And then when we press play, what we should see is everything start to collapse under gravity, because the solver's doing its thing. You know, they've bubbled up just what we need from DOPS to here into SOPs. And you'll notice actually, if you select this node, the RBD Bullet solver, there's loads of settings that they've given you so you can control your simulation. Now the first thing we notice actually is, look, they're all falling through the floor. The reason our bricks aren't falling, if you remember, is we made some of these passive, so everything else is kind of resting on those. But you'll see our doors falling through. There is no ground plane there, so we've got a couple of options. The first option is we can either go to ground here on the RBD Bullet solver node. There is a tab for ground, so that's in the solver tab. And then we can click on the ground tab, and we can add a preset ground. You could even plug in a height field if you wanted. You can just map it there, or just a ground. And this is just an infinite flat plane. Or if you wanted to plug in your own geometry, you could just, for example, make a grid and just plug that into this fourth input, the collision geometry. Let me turn off ground plane. And look, you'll see if I hit it in wireframe, there's my grid as a blue collider. If I just make that bigger, we'll see we can scale that up. And we could use that to collide with instead. In fact, the visualizer slows it down a little, so I'm going to click on the rigid body solver node here, click on the visualize tab, and we can turn off show collisions. So we're not displaying that. But now if I press play, it's going to collide with that ground plane, and you'll see they don't fall through the ground anymore. So hopefully the bits will just, there we go, they're seeing them start to collapse, but they're not falling through the ground. And there's no glue holding them together. That's all good. So what I want to do now is create a force to explode this with. So we've got our basis of our sim, we've prepared everything. We can see if we press play and we've removed all the constraints, everything's collapsing and breaking up as we want. You can see sort of the nice glass shapes and the wood shapes and all the bits that we defined a lot earlier. So let's create a force of which we can blow this up with. So a traditional way really is to start with a sphere and just sort of make a noisy sphere and use that. Let's template this constraint node so we're not templating the sim. And we'll use this as the basis of our velocity vectors. So we want a load of radiating vectors shooting out, and we want to control those. So this is the way I like to do it, or one of the ways. When we come to use this for Pyro, we'll actually change this for one of the new Houdini 18 tools, but I'll show you that nearer the time. But for now, I'm just going to create a quick proxy one with the sphere. So this is one way to do it. So we have a sphere here. Let me turn on the smooth wire shaded, and that's a primitive. So let's turn this to a polygon. Maybe increase the frequency quite a bit. And I only want half this sphere. I don't want any forces radiating under the ground. So I'm going to make a clip SOP. And the clip SOP will allow me to clip the geometry based on a plane. So based in the Y direction here, and I can move that up and down the Y direction. But 0 is essentially the origin, and look, we've clipped our sphere in half. And we don't want it nice and smooth and radiating. We want to add a bit of noise to that. So we'll add a mountain SOP. That'll just deform it a little. So yeah, I kind of like that. We've got a bumpy sphere, and you'll see it's inside the house here, so it's definitely going to explode quite nicely. And then what I want to do is scale this up and down like an explosion. So I'll create a transform node to do that. And what we'll do is we'll just set the uniform scale to 0, and maybe go to frame 3. Let's set a keyframe. So let's right click, choose keyframe, set keyframe. So and then what we'll do is we'll maybe go to frame 5. So let me just step forwards for 5, and then we'll set this to a 1. Change that to 1. Right click keyframe, and then we can choose. Let's do that again. Right click keyframe, and then commit change. There we go. So our sphere just suddenly appears, whoosh, like that. So I'm going to create some velocity vectors based on this, and that's easily done. We can use a trail SOP. So a trail SOP will plot the point positions and calculate V for us if we set this here to compute velocity. If we go to wireframe and turn on display velocity here, we'll see those vectors. It starts off as 0, and then when it stops moving, they set to 0 as well. So we've got those kind of rushing through, which is quite nice. And we could actually add a bit of noise to that if we wanted. Let's see where those vectors are. Here we go. So to add a bit of noise, we could add on top of this a point velocity node. So not only do we have the velocity based on the motion, we can also add a bit of noise with this point velocity. So you'll see it just keeps the basic value coming through. And then we can go to curl noise, and we can add some curl noise on top of it. So you can sort of add a lot of noise and disturbance there. If you bring down the pulse, it goes a bit quicker, and you can change the scale with swirl size here. So we just add a bit of noise to that. Now the downside of this, if you look, when we're at 0, we actually have some velocity now. And when we've stopped, we still have some velocity. So if I look at the spreadsheet, you'll see V has a value when it stopped moving. That's because of the noise. What we really want to do is animate that noise on and off with the same of the scaling here. So what I'm going to do is, where it says uniform scale, I'm going to right click and copy parameter. And in here, on the point velocity, in the scale, I'm going to right click and paste relative reference. So that's going to scale it up and down the noise accordingly, and then I can multiply that further if I want. So I'll add a lot of noise to that, and you'll see oh, that hasn't gone to 0 again, has it? Oh no, because we didn't scale it to 0, the thing. Let me just delete that channel. Instead of copying relative reference, this time we can right click and actually paste channels and expressions. What that will do, it'll actually copy in our curve. Look, if you click on it now, it says Bezier. So if you hold down shift and middle click on the word scale, this will bring up the animation editor, and you'll see your keyframes there. So to bring up the animation editor, hold down alt and middle click on the word scale, and that will bring that up. So not only can you copy channels across, you can copy entire animation curves. So what we really want to do is actually not really see that. If we go to frame 5 where it's 1, we can go to frame 6, and then we can set the curl noise to 0 and just set another keyframe. So basically copied in the animation from the transform, but then we added another keyframe at the end, which just set that to 0, or you could manually keyframe it, whatever you want. The important thing is that in our spreadsheet our velocities must be 0 on frame 6. So we still have velocity on frame 5 but not 6. That's important to remember. Excellent. So we're managing that. So I'm going to create a null, and we'll call this forces out. There we go. So we can read out our velocity or our force out or whatever. So how do we apply that to our simulation? If I was doing this properly inside DOPS, then I'd go inside DOPS and import these points in and manually merge them in. But since we can't do that, we have to do everything at this level. So if we look at the parameter pane here by tapping P for the RBD Bullet solver node, if you go to the solver tab here and to bullet objects, this tab here, see my flashy cursor, you'll notice that we've got this thing, overwrite attributes. So this means any attributes that we've overwritten. Remember, we changed the active on our bricks to make some active and some passive. So it's going to override them every frame instead of using the ones from the solver here, which is pretty cool. So what we could do is bring in our own velocity. Now, how do we do that? Well, first of all, we've just got to type V in here because that's the attribute we want to bring in. And then what we want to do is transfer the velocity from this branch onto our bullet objects. Now remember what I said was, let me just pop a null in here. Remember, this first output is the geometry that we're actually going to render. And if we middle click, there's none of the bullet attributes. Now if we look at the last one, this is the bullet objects or the proxy. This is what bullet's actually going to simulate with. If we middle click on there, we can see those bullet attributes, things like density and bounce. So it's this geometry here that's actually, it's going to be looking for these attributes. Remember, active, it says active. So it's on this branch we want to transfer the attributes in. So let's do that. Let's use an attribute transfer. So where's my attribute transfer node? There it is. Let's get rid of that null. So I can branch this over like this. And let's plug in the force to the attribute transfer. I'm going to turn off primitives, and I'm just going to tick on velocity. So only bringing velocity in. And always the condition, this distance is way too big. So let's bring that down to something like 3. It's always too big to begin with. So whenever anything's within 3 units of this, it's going to pick up that velocity. So let's go back to the bullet solver. Let's go back to frame 1. Make sure we have V here. So now we've transferred, if we middle click, we can see we've got V being transferred in. And we're going to override it every frame from the one in the simulation instead. So if we press play now, so remember, nothing's glued together, so it should just fall apart. And when our force kicks in, there we go, we can see our velocity kicking in and moving everything, and then it kind of just hangs there in space. The reason it hangs there in space, let me just stop that, is quite simple really. We're overriding the simulation velocity every frame. We're not adding to it, we're overriding it. So basically, when our velocities here, if I look in the spreadsheet, becomes 0, we're overriding the velocities in the simulation with 0 every frame. So it's the velocities that move everything. So if you're telling it 0, it's going to stop moving and freeze like this. Bit of a problem. What we need to do really is tell this either to add the velocity in rather than overriding it, which we can't do unless we dive inside DOPS, or we can actually keyframe this on and off. So we can have this overriding the attributes until the last time we have some velocity. So again, if I bring up the spreadsheet and just look at this node, so if I step forward, we'll see that the last frame we got velocity is frame 5, and then frame 6 this is 0. So what I want to do is I want to keyframe this, that on frame 5 it's on, and then frame 6 it's off. So at frame 6 we're not reading in the zeros, but we're going to keep or preserve the velocities from the frame before. So let's try and do that. I'm going to come down here and set this to manual at the bottom right. Remember, we did that before. So from auto update to manual. So this is, as I move the keyframes, it's not going to try and process this node. So we'll go to frame 5, And then on the tick here, you can right click, go to Keyframes, choose Set Keyframe. And if you go to frame 6, you can turn it off, right click again, go Keyframes, and then let's try that again, right click, Keyframes, and then commit change. So if you go between frames 5 and 6, you'll see the tick appear and disappear. Let's see if that worked. I'm going to set this back to down in the bottom right. It's going to set it back to auto update. And then let's press play and see, because we're now overriding with the velocity until the last time the velocity is there. And then hopefully the 0 will kick in after the keyframes. Bang, there we go. So it keeps moving. And there we go. We're not transferring in the 0 at any point. And it's able to keep the velocities from the frame before of the sim. And it basically inherits those over. And we can see our house now explodes quite happily. Excellent. So that's how you can kind of bring in velocities and control exploding things inside your rigid bodies easily. And we can use this sort of velocity force to drive our pyro later on. Excellent. So we got that working, but the problem is this is not glued together. So let's pop our glue in and see what problems that causes us. So now if we press play, we only have velocity coming in there, but our glue, our constraints don't know that they need to break. So if we just wait for that, you'll see we've gone past the ticks and nothing has changed. Because we need to add another attribute here. So there's a really nice attribute with the glue. If I just step forwards a few frames, and we'll just make a null, so I can pull off these constraints here. So I can see the constraints. And if I just look at the spreadsheet to see the attributes on the constraints, remember you have to go to the primitive attributes for this. We'll see we've got some that we can play with, like force and impact and stuff. Now impact's the interesting one. The impact is what drives the bullet here. When the impact here is above this threshold, then it will break the glue. And when it's below, it won't break the glue. And that's kind of a hard built-in feature. So we just need to create an attribute to control that breaking of the glue. So how can we do that? We need to create sort of an impact attribute. Well, we know the kind of velocities or forces we're dealing with here. If I just display the velocity vectors in wireframe, here we know they're strong when it's moving quick and then they fade off. So we could use the velocities here to create an attribute to drive our impacts, and that's exactly what I'm going to do. I'm going to make a point wrangle here, and I'm going to create a new attribute called f at impact, because I just want to bring this one in to break the bricks there. And we'll say that is equal to, now we'll type in length bracket v at v. So this is going to give us the length of the velocity vector. In other words, the magnitude of it. So if I do right click spreadsheet on this wrangle, we can see that the impact is measuring here, there, the size of the velocity. And as the velocity gets bigger, this impact gets bigger. And we can see it's in the region of sort of 9, if I just sort the numbers, for about 15 seems to be the maximum number there. Something like 15 is our range, and they're quite smaller impacts. So let's look at how we can wire that together. So we need to tell the simulation about that impact. And what I really need to do, if you notice the impact are on the primitives here of the constraints. Remember that's where the impact attribute is, on the constraints here. So if we look at the spreadsheet, remember they're on the primitives there. So I can't just attribute transferring, because this is not the attributes from the constraint there. So the way we can do this actually is we can select these breaking thresholds in the solver, and we can drive it through here. Let me just display the geometry again. So we can do it through here in this breaking thresholds section. And at the moment we're breaking all the soft and hard constraints. We don't have any called that, so let's remove that. What we do have is constraints here called glue. If you look at these configures, you'll see they're all set to glue and glue, that kind of thing. So here we're going to affect all those glue constraints. Let me actually display the constraints with the null again. So we can break them on demand. For example, look, I can break them at a certain frame. So let's say frame 2. So if I go to frame 2, that'll just break all the constraints with the name of glue. There you go. On frame 2 they all got removed. If I turn that off, then they'll all stay there. So I can put in some controls here, and look, it says delete constraints. It tells you what it's going to do here. So look, if I go to frame 2 now and frame 3, they're not being removed. Now remember, we did call them all glue, but we gave them all their own groups as well. So in here you can actually specify the group. So you can say, look, just the door glue, and then you can make another tab for the other glue on the other things. Or you could give the glue unique names. It's up to you. There's many ways to do that. So this is affecting all the glue. I want to affect everything here. I want this to all feel the impact of that explosion. So how can we drive that in there? Well, we need to use basically a bit of an expression, really. We need to come here and use this vex expression down here. Because what I need to do really is read in the impact values from here, these impact values, and get those to transfer onto the actual constraints here. So the way I'm going to do that is with an expression called near point. So the near point expression allows us to look at a point in this geometry, and this geometry is going to be the constraints, and then we can say find the nearest point in a neighbouring geometry within a certain distance and tell me what the attribute value is on it. So it's like an attribute transfer, but we're writing it in code, and that's what we're going to kind of do here. So the near point expression first of all wants a maximum distance parameter. So we'll type float max dist, and we'll set that to 3 units like we did with our attribute transfer. And then what we've got to do is type the near point expression. Now the near point expression will return the number of the nearest point to the constraint that we're dealing with. And what we want to do is then take that point number and then use the point expression to find out a value of a particular attribute, in this case the impact attribute, and then we'll copy that value onto the impact attribute on these constraints, and then hopefully if it's big enough the glue will break. Now you'll notice this type text here. What I can't do is actually type a path to a node in my expressions in this particular wrangle. You need to follow this. Look, the second input, so if I type a 1, which will be the second input, that's actually the packed bullet geometry. That will be this first, or rather this third. I can refer to the data in this third branch. And if I do third input, which is, if I write in the code, that will be 0, 1, 2. Remember, we count from 0. So third input will be 2 as in the index number. And that will refer to arbitrary SOP geometry, anything I plug in. And that SOP geometry refers to anything you've plugged in down here. So I'm going to drag this null down here. And now I can refer to this as input 2 in my coding. So whenever I write a 2, I'm referring to this path, which will refer to this node. And I can read these attributes, including impact here, which is the one that I want. So now that I've put that path in, I can write the next bit of the expression. So we'll say int for the point number, pt, so that's our point number, and then we'll say near point, and then we want to ask it which geometry we're looking for the near point. That's number 2 here, that forces out null, and then we type in at p, so this is the current position of the part of the constraint we're looking at. So we're picking a point on the constraint, that's the at p, and then we're looking for the nearest point on that forces out geometry. And then what we want to do is ask it to look only within the max dist that we've just specified as being 3 units. So it's only going to look for points within 3 units. And that's going to return the point number. We then want to find out with that point number the value of the impact attribute on that point. So let's type float impact, and that's equal to the point expression. So again, we're going to ask for the input geometry that forces out, which is referred to as number 2 here. So we ask it for the attribute we want to read, that's also called impact, and then we give it the point number. So we just found out the nearest point, that was pt from the expression above. And then what we want to do is take that impact and add it to the actual attribute. So the actual attribute is f at impact, and then we can say that is a let me type that incorrectly, impact. There we go, and that's equal to just the variable that we made, impact. There we go. So that should work. Here we've got we're defining the distance as being 3. Here we're using the near point expression of input 2, which is this guy here, this null, and then we're saying look at your current position of the locator, and within 3 units, is there a point? And if there is, store it here. And then we're using that point number here in this expression to return this attribute from it, which we're storing in that variable, and then we're just returning that into the actual attribute on the geometry, which the solver will read. And if this number's above the breaking threshold, then it will delete the glue for us. So let's see if that works. Now, it may not work, because if we look in our spreadsheet, if you remember on this forces out null, our impact only really gets up to 15. Now, my glue, if I look at my glue, we haven't changed any of the glues. They're up at 10,000. So I need this number to be above 10,000, or a way to control it. And we can do that here in this wrangle. So very simply, after this length here, we can type multiply, and then CHF, and then we'll call this impact scale. So we have a scalar there. You'll notice it's gone to 0 because we've got to click on this magic button here, and then we can type a 1 in, and we'll get back our 15. If we do 10, we'll get our 143. And I'm going to do it by 100 now, so we've got our 1418. If I do it by 1,000, we've got 14,000, which is above our 10,000 that we need. So hopefully that's enough of a force to break our glue. So let's preview our rigid body solver now. And we're bringing enough of this impact that hopefully that will feed through and actually break the glue, and then the other velocities will kick in. So we're doing it in this way because we need to transfer these attributes onto the constraints there. And look, there you go. Look, it broke the glue, or it broke some of the glue. Because remember, not all the forces were up that high, some weren't. But look, we've got an interesting breakup now where the glue is actually fractured based on our impact. And then if you look, the rest of the building is exploding outwards. So that's kind of good. We can kind of scale this down a little. What I'd like to do really is work in the realms of hundreds. Mind you, it depends on the forces you want to hit. Yeah, we'll keep it in the realms of the 10,000s here. So I'm going to leave that at 10,000, knowing that what's our peak again? Let me just turn this null on. Let's do a spreadsheet. Look in the point attributes there. So yeah, our peak was up at sort of 15,000, that kind of thing. So we're peaking at 15,000, and the lowest is 7,000, which is not breaking anything. So we're going between sort of 7 and 15,000. So let's try some of this out. So I want my glass to easily break. So we want this sort of less than 7,000 really. Let's put 5,000 in. We'll keep the glass to the frames quite high. Also, the frames to the walls, we'll make that also quite low, so the frames will pop out. So that's below the lowest force, so that'll always break. So on the all door constraint, this is holding the whole door together. Again, we'll break. We'll make that lower than 1,000, lower than the 5,000, so that'll easily break. But the wood grain here will make really high, so the wood will never splinter. Will come apart in separate bits. And we'll just take a 0 off the door, so it will come off the hinges very easily. Now the bricks here, we've got 15,000, isn't it? Let's put 11,000, so some will break and some won't. Now our roof tiles, this will be interesting. Let's do all the, this is all the roof, constraint to all the roof. So again, we'll make that low. And then, like I said, on the actual fractures here, let's maybe make that 13, so not all of it breaks apart. And we'll just drop the where it's constrained to the roof a bit lower, so it'll easily come off. So the roof ridge tiles here and the actual concrete tiles themselves, I've made that quite high, so hopefully they won't break and stay in as single tiles. Whereas where all the tiles are glued together, I've made that quite weak, so the roof should come apart. And here I've made quite weak, so the roof should come off the bricks easily. I've made the bricks quite between our thresholds, so some will break and some won't. And I messed around with the doors, just to recap. So I've made the overall door constraint quite weak, but the individual splinters very strong. So hopefully we'll see it break into planks rather than splintering. We made the glass very weak. Let's actually take off another 0. But we kept the in the frames quite strong, so hopefully some shards will stay there. And then we made the some of the frames will come off the bricks quite easily. So we've varied quite a lot as we go down around the thresholds that we know that our impacts are running through. So let's just press play and see the result of that tweaking. So hopefully as we go through we should see some interesting things. So look, there we go. If I just stop it for a minute, we'll see what we wanted, hopefully. So look, we'll see that the glass just gets pulverized and shattered very easily. We'll see that the door falls apart into its planks, but the individual planks don't shatter very well. You can see the frame got shattered around that. And yeah, look, the frames came out, some frames came out from the windows quite easily. And the bricks didn't break apart very easily because they were at the top end of the threshold. And if we look at the roof, again, like I said, the roof overall structure broke up, but the individual tiles didn't. So if I want the tiles now and the bricks to break up more, that's very simple. I can now go to my bricks and just bring down this threshold. So I know if it's about 7,000, pretty much it's all going to break. And same with these roof tiles. So this one was all the roof tiles again. So let's put this maybe at 800. So some will break and some won't again. And actually, let's go to the door and let's let those splinter this time. So if I just take the woodcut grain here, again, we know it's between 7,000, so maybe we'll make 7,500, 8,000. So maybe some won't break and some will break. So again, by setting it up like this, you can see how very easy it is for me to change the glue properties and get quite a different look and control sort of how each material should break. So if I do that again, we'll see now that the windows are still shattering, but look, the door now, not only has it come apart in planks, but now it's started to splinter as well, which looks really nice. Look, we're getting that nice sort of splintering in between the planks. And we'll see the roof now, even though we've got the individual tiles, a lot more of those tiles are being broken, which is really nice. And we get this sort of nice, and you'll see all the bricks totally have been pulverized into their clusters. Maybe I'll just increase the bricks a bit more, maybe 8,500 or something like that. Now there's another thing we can do actually on the Bullet solver. Sometimes these pieces go a bit wild, so we can actually go to where is it, on the solver node on forces. We can actually add some drag and some drag spin. This basically just adds some air resistance to those pieces and stops them going too crazy or wild. So I'm quite happy with the way this is going. What I will do is, let me just plug this last null in, and then let's turn on the smooth wire shaded. And what I want to do now is just, let's just save it, is to flipbook this up so we can see how the simulation's going to look. So to flipbook, I'm going to right click on the flipbook icon here and bring up my new settings. And I'm just going to turn the resolution off here, so it'll do it the size of the window. And I'm just going to hit start and let that run through. So I'll pause the video while that caches up. So now the flipbook's complete. If we press play, we can see that it explodes quite nicely, and it goes out quite a way. If I just zoom out a bit more, actually, we can see that it blasts out all those pieces for quite a distance. Maybe I'll just run that flipbook up once the last time. Now we're a bit further away. And so we can see that we can control the velocity in, we can control the impact, and we can control sort of the fracture shapes we get, and also the strength of the constraints really does make a big deal. If I just go back here, again we can see the door breaking up the way that we wanted by managing the constraints there. And again you see you get quite a nice explosion that suggests that house is blowing up. And we'll use this as the basis for our Pyro Sim. I won't actually use this, we'll set it up slightly differently, but we'll check that it works with this. But I'm quite pleased with that. One last thing, if I did want to scale the velocity, if we look here on our point wrangle, you can see we made the impact and we've got a control to scale the impact here. What I'm actually going to do is create another one, so maybe I can tone down that velocity or scale it up at this point. So if I thought it was too strong, I could tone it down, or vice versa. So that's easy. We can say v at v equals v at v, and then times, and then we can again just type chf, call this velocity scale. Don't forget your semicolon, and when you click your magic button here, you'll get your scale there. So if you put it to 1, it'll be what we just saw, which I quite liked. Maybe I'll just bring that down a bit, maybe 0.9. So interestingly, what we should really do is do this after this guy here. So these are truly independent, otherwise when I scale the velocity I'm going to be scaling the impact too, whereas if here I'm reading the impact first and then I'm going to scale up the velocity afterwards. So it's better to do it that way these two are totally independent of each other. So just a quick sanity check. If I press play now, I should have a very, very similar explosion, just without those bricks flying quite as far. We might not notice 10% less velocity when it explodes, but there we go, it's exploding happily now. I haven't sort of affected the impact scale, which is really kind of cool. So again, actually that's going to affect all my nice glue, but we're going to come back and tweak all this when we create a slightly different force in there. So say you're happy with all of this, where do you go next? Well, the last logical thing really is to bake this or cache it to disk, because once I cached it to disk I can then use it as a collider for my pyrosim. So even though the pyrosim will inflate with the same kind of explosion, but I want it to collide with these bricks to suggest that it was actually causing that explosion to begin with. So I want to cache this up. So again we use our RBD IO, so that's very good at caching all these things up. And again we can, if we want to cache up all the geometry, we can plug it all the way in like this, which I'm going to do. And then let's colour this one blue as well. And this one will write out the entire simulation. So in this case I do want to do the frame range. In fact, I don't want all 240 frames. I'm going to select the frame number here at the end and let's do 75. We'll only worry about the initial bang. So there we go, and you'll see here we're only going to write out 75 frames of cache. So I'm just going to change the name here. I am going to leave this $F because that'll be the frame number, so then we'll get one frame for each, one cache file for each frame, which is the best way to go. And we'll call this house explode. We'll version it, version 1. There we go. So all that's left to do now is save the scene and hit save to disk. And what that'll do is that'll process that. It goes quickly because I've still got some cached, and then it will write out all those 75 frames to disk. And obviously if you change anything you're going to have to re-cache it all again, but I was quite happy with what we saw, and I think that's good to move to the next stage, which would be to actually rebuild this in Pyro and get the Pyro sim to work with this before we then try and render everything. So it looks like our house is exploding. So there we go, it's written out all our 75 frames. That was fairly quick. And then once this is done here, the last thing I'd want to do is click on load from disk over here to load back in that geometry, and then we can just check it by flip booking it if we want to. And like we saw in the other RBD IO nodes, you can choose up here what data you can get it to write to disk for you. So I'll just pause the video while that catches up with us. So that's finally caught up with us. If we turn on load from disk, it will now read in that geometry. So if I just pop in a little null here and look at the actual geometry that we want to render, we should be able to drag through backwards and forwards, and we'll see it's reading that explosion back from disk for us. That's excellent. That's exactly where we want to be. So let's just turn that on. I'm going to save this scene, and what we'll do in the next video is we'll set up our pyro with a similar force, and then we'll probably recache this out and we'll look at how we can add pyro to the equation and make it look like our explosion has destroyed our building.